much of what a computer can do depends upon what its CPU, the central processing unit, can do. And what a central processing unit can do depends upon what instructions it can execute. The set of instructions that a CPU can execute is called the instruction set of the CPU or of the machine. The user view the instruction set as a definition of the machine. The designer view the instruction set as a functional requirement for the machine. Today, let us study the instruction set. Let us come to the program that we shown on the first day, okay, a high level code where we have written only 3 lines of code, read xy, z equal to x plus y, and print z. Okay. As I told that these statements will somewhat vary from programming language to programming language. Now, as I said, that this high level language code cannot be executed directly by the machine, and therefore it is translated first into an assembly language code, where say readx is converted into assembly language statement that in a input statement which reads an input into the accumulator. We are thinking of in terms of a accumulator based machine, okay, and then that it has to be stored into the location x, therefore it is stored accumulator x. Similarly, in and stored accumulator y for reading y. Now, this is a computation that is done since it is an accumulator based machine. First x has to be loaded into the accumulator by this instruction, load a accumulator x. Then I say that add memory y, that means content of y has to be added to the accumulator, and then content of the accumulator has to be stored into the location z by means of a store accumulator z, and print z is basically out. We have assumed that only one input device is there and one output device is there. Now, I have shown this that assembly language statement, but the assembly language itself once more cannot be executed by the computer, the central processing unit. It is further has to be translated into what we call that machine language code. Now, this is the machine language code we have written in hexadecimal notation. For example, in has a code of 01, okay, which essentially means this is hexadecimal 01. The code actually is say 0000, then 0001. This is 0, this is 1 in hexadecimal. We have written this for our ease of writing, okay. Now, similarly, stored accumulator, the instruction is 04, and the address of x has to be specified in that, and therefore the address of space we have specified to be 0500. That's also in hexadecimal. We have given all of them in hexadecimal notations, okay. Now, this is address of x. Now, you see that essentially a high level language statement like this or this is ultimately converted into machine language form, zeros in terms of zeros and ones, okay, and it is executed. The correspondingly we have an assembly language, right. This is for human consumption. For example, this is for human use. This is also for ease of writing programs in almost machine language. We call it assembly language. There is a one-to-one correspondence between assembly language statement and a machine language statement, okay. Therefore, when we will discuss that instruction set, instead of directly using machine language code, we will discuss in terms of somewhat assembly language code. Assembly language code is nothing but a symbolic mnemonic representation of the machine language code, almost code for code, okay. Now, why I have shown this is this, that you see that every instruction, okay, right, has an instruction format, right. For example, this particular machine, that instruction format for storing an accumulator x is STX, okay, I mean assembly language code is STX, and that instruction format is say 04 and 0500, okay. This is the instruction format in the machine language for this STX code. Now, if we examine it, you see that it can be divided into the instruction, machine instruction can be divided into two parts. One is the operation that has to be done, and we call it op code, okay. And another part is that with what the operation has to be done, we call it operand address, okay. Therefore, one part is opcode and other part is the address, okay. Now, depending upon the machine, this instruction format, as we call it, this instruction format varies. For example, the machine that we are considering is a single address machine, so to say, which means an instruction can have at most one address, okay. For example, this doesn't need an address, this has one address, this doesn't need an address, this has one address, okay. Therefore, we call it a single instruction single address instruction. Now, similarly, we can have, say, double address instruction or triple address instruction. For example, that a double address instruction may take this form, that add, say, x, y. That means you add the content of x to the content of y and then leave the content, leave the result of addition into y. That is a double address instruction, okay. Similarly, a triple address instruction can be, say, add z, okay, sorry, add z, y, x. That means you just add y with x and then store the result into z. We call such a instruction a triple address instruction. Now, depending upon the machine, that machine can be a single address, it can be double address, and it can be triple address also, though the double address is more prevalent, okay. Now, as you can naturally assume that if we have a single address instruction, there should be some zero address instruction also. Well, there are. When I say that it's a single address machine, instruction machine, it means that at most there can be one address, okay. Therefore, it can have some zero address machine as well, okay, zero address instruction as well. Similarly, a double address instruction machine can have a single address instruction and zero address instruction also. So for triple address, that it can have double address instruction, it can have single address instruction, it can have zero address instruction also, okay. And apart from this, that we can somehow and sometimes manage the operands in such a way that we don't need to specify the addresses to compute something. We'll come to that discussion later. Now, therefore, when I call that instruction format, I say that it has an operand address. If it's a double address, there will be two more operands here, okay, sorry, one more operand here, right, say operand 2, and if we have a triple address machine, then we'll have another operand which is operand 3 over here. and this is the opcode. Now, one important thing, so far as that instruction format is concerned, is that how lengthy will be an instruction. Okay, naturally that depends upon the number of operands that you use. Okay, and also the size of the opcode and the addressing scheme, okay, that you use here, here, and here. Okay, that means the addressing scheme that you that the computer uses. Now, naturally, the size of the opcode will be dependent upon one factor is that if n is the number of instructions that you have to implement, then the size should be at least log 2 of n, upper bound of it, okay, naturally. And it should also, the opcode size here we have shown to be 1 byte only. The opcode size also will be dependent upon that what way you use opcode. That means sometimes that the way of specifying the address, for example, way of specifying the addresses here is totally independent of the what operation that instruction does. Okay, in such a case, we call that it is an orthogonal instruction set. Okay. Orthogonal that orthogonal instruction set, as I said, that it is essentially the way of specifying the addresses of the operands is independent of the opcode. Okay, for any opcode you can use any kind of operands. Okay, in that case we call it an orthogonal one. Now, if it's an orthogonal instruction set, then the opcode may be somewhat less. Okay, and in such cases the opcode can be of fixed length, right? But if the opcode also specifies, the opcode has to specify, include where the operands are. In that case, the opcodes are generally of varying length. Okay, therefore, that instruction opcode can be of fixed length, can be of varying length, depending upon that how the machine instruction and decoding has been designed. Okay, once more we will have some little more discussion about it later. Another important factor of the length of opcode and the length of instruction is that the word size. Okay, we know that the minimum unit, addressable unit of the computer is byte. Now, 2 or say 4 bytes is taken together and is formed a word. Okay, and generally an instruction will be, and word will be an integral multiple of an instruction, or an instruction can be an integral multiple of word. Okay, that way that instruction set size, instruction length is decided, and the designer takes all these issues into consideration when they design an instruction set. Now, let us, after we have come to that what is an instruction format, that it has two parts. One is that opcode part and another is that operand part. Okay, let us see first the opcode part of it. Essentially, we'll see that what operation a computer can perform and the CPU can perform or generally performs. Okay. Now, the total instructions are of various in nature and generally are grouped together, okay, under different heads. Okay, let us go head by head, okay, and give some examples of the instructions that a computer performs. Okay, first, naturally, is that data movement instructions. Right? We call it. Say, first group is data data transfer group. Okay, essentially this moves data from one point to another point. Okay, now as I said earlier also that the computer in the CPU, there are some general purpose registers, okay, and the data has to be moved from memory to the inside of the CPU, that means in some register within the CPU, and data has to be moved from register to register also. Okay, the codes generally are of the form that say, we can say move, say from register 1 to register 2. That means we move the data from register 1 to register 2. I am using a two address machine, okay, to give examples. Okay, uh, naturally the single address machines or the triple address machines almost follow the same set of instructions, only the addressing will change. That we'll talk about later on. Okay, the move can be from a register to register. It can be from memory to a register. It can be from register to register, and it can be from memory to memory. Now for the data transfer group, okay, now takes care of such transference of data from register to register, memory to register, register to memory, and memory to memory. Not that all of them have to be there in all the machines. Okay, for example, that in the case of a single address instruction, that memory to memory, that movement is not there. In that case, one has to move the data from a memory to a register, and then from a say memory 1 to a register, and then from register to memory 2, that way. But the move data from one point to another is a very important instruction that has to be there in some form or other in every machine. For example, that instead of move, some machine can also say transfer, say TSR. I am talking that this is the assembly language, corresponding machine language code will exist. Therefore, we talk in terms of assembly language only. Sometimes there are what we call that exchange instructions is there. So for example, if you say that exchange R1, R2, okay, that means data between R2 and R1 is exchanged. That also falls under that data transfer group. Okay. Now that's our data transfer group. Let's see what other groups we have. Say 2, it is another important group of instructions, say arithmetic, group, right? In this arithmetic group, actually all addition, subtraction, multiplication, division, all of these instructions should be included, right? Now this addition, subtraction, multiplication, that can be done on integers, that can be done on floating points also, okay? Naturally, that instruction set also will be dependent upon what are the data types that are supported in a computer. The general data types that are supported in a computer, as we know already, that it is integer, floating point, it can be character, or it can be logical data also, okay? Now say that arithmetic group therefore can have add, that means adding two numbers, subtract, okay, multiply, divide, okay? These are basic operations, say on integers. Then on floating point it can be say floating point add, floating point subtract, say floating point multiply, and floating point divide. That works on floating point operands, okay, and uses the floating point arithmetic unit. This uses the integer arithmetic unit, okay. Now there can be instructions for increment of a content of a memory or a register, decrement of a content of a memory or a register, okay. These are generally on integer operands, okay. Then we can have say abs for determining that absolute value, and we can have negate also to take the complement of a integer number, okay, or the negative of the floating point number. Therefore, these are mainly and generally the instruction that are there under the arithmetic group. Okay. Now let us come to the third group. Okay, we call it the logical group. Okay, under this we have the instructions generally like say and, or, exclusive or. Okay, and these are on bits. Therefore, by that I mean, for example, say, let me explain, say AND operation. Okay, say this is our AND operation. Say this is operand bit 1 and say this is operand 2. Both of them are 1 bit. Okay. Now, if it is the operand 1 can be 1 or 0, this also can be 1 or 0. In the case of an AND operation, that if both operand are 1, then we have 1 here, other we have 0, 0 and 0. Okay. Therefore, when we do that AND operation, say on 2 bytes, the 2 bytes will have, say, 1 byte contains this data, another byte contains, say, this data. Say this is my operand 1 and this is my operand 2. Then AND operation will be performed on bit by bit. Okay, which means the result will be 1 here, 0, 0, 1 here, 0, 0, 1 and 0. This will be op 1 and op 2. Okay, that will be the operation of op 1 and op 2. Okay. Now, similarly, in the case of an OR operation, bit by bit that operations that will take place is that if it's 1, 0, 1, 0, then if any, this is operand 1, say, this is operand 2, then this will be 1, this will be 1, this will be 1 and this will be 0. That means if both of them are 0, then the result is 0, otherwise the result is 1. And once more, it will be operated, okay, bit by bit. For example, this is operand 1 and this is operand 2, then the OR will be, this is 1, this is 0, this is 0, 1, okay, 1, 1, 1 and 1. This will be our operand 1 or operand 2. Okay. This is operand 1 or operand 2. Any of them 1 is 1, otherwise it is 0. For example, here it is 0. Now, similarly, that exclusive OR we can define this way. Say exclusive OR operation will be once more bit by bit. Say operand 1 here, operand 2 here, 1 and 0, 1 and 0. Exclusive OR says that if either one of them is 1, then the output is 1, otherwise the output is 0. For example, here this is 1 because this is 1, this is 0, and here this is 1 because this is 1, this is 0, and here both of them 1, therefore it is 0. Here also both of them are 0, therefore it is 0. That is our exclusive OR. And once more it will be performed bit by bit. Okay. For example, that exclusive OR operation of these two will be, this is 0, this will be 0, this will be 0, this is also 0, this is 1 because this is 1, this is 0, this will also be 1, okay, this is 0 and this is 1, okay. This will be our operand 1 XOR operand 2, okay. Now, these are the instructions that generally are there, for as logical under the logical group. There's few more. For example, compare is a instruction which compares two numbers x and y and accordingly decides which one is greater by appropriately putting a flag bit, as we have talked about the flag bits earlier. Then we have that which we have already used in our arithmetic operations. Okay. Arithmetic shift right or arithmetic shift left. For example, if we have a number, I'm taking a 4-bit number for our convenience of representation, say 0, 1, 0, 0. The arithmetic shift right, say this is a sign bit, and I'm talking about, say, in terms of 2's complement, right? That arithmetic shift right will be essentially that I shift one position to the right, therefore it will be 0, this will be 0, this will be 1, this will be 0, and the sign bit will be repeated here. Okay, that is our arithmetic shift right, which essentially means that whatever shifting is done, okay, that the sign bit is repeated at the sign bit position. Say if it is a negative number, say 1, 1, 0, 0, if we give a right shift to it, then it will be 0 here, 0 here, 1 here, this is 1 here, and 1 is repeated. This is our arithmetic shift right. Okay. Now this bit that flows out can be captured in a 1-bit register and can be kept for examination by the CPU once more, right? Similarly, we can have arithmetic shift left. We can have logical shift right, okay? Oh, this is spelling mistake, shift. Logical shift right or logical shift left. In this case, that irrespective of the sign bit, what enters into the most significant bit in the case of a right shift is zeros. Okay, we call this as a logical shift right or logical shift left. Sometimes we can have a rotate instruction also, say rotate right or rotate left, okay, and that can be either straight or through carry bit, okay. This can also be through carry bit. That way we mean that, say for example, if we have a data, say 1001, rotate right means that, so rotate right, that it will be rotated right, and the bit that comes out of the rightmost position enters into the leftmost position. Therefore, rotate right of this will be, say 0, 0. Okay, this one comes here and this one comes here. That is the rotate right of this. Okay, and it is, if it is rotate right through carry, right, in that case, say if the original is 1001 and we have a carry flag, okay, which was containing, say 0, then this one comes into the carry, this 0 comes as the most significant bit and the other bits are shifted to the right, which means the result will be, say, after this rotate right operation, 1, 0, 0, okay, this one comes here and this 0 comes here. Therefore, say this will be the content of this operand and the carry will now contain this one that comes into this location from the least significant bit. That is our rotate right operation. Similarly, we can have rotate left, and rotate left through carry. Okay. Now these are our that logical operation, and we get the complement operation. That means complement. We take generally once complement. Okay. Is an operation which is also is grouped under our logical operation group. Okay, which means if we a 4-bit operand, if we have, assuming that a 4-bit operand we have 0 1, then complement will be 0 1 1 0. Okay, that will be the complement, one's complement of the original number. Now, apart from that, we can have few what we call that input output instructions. These are typically for inputting from an input device or outputting into an output device. The simple input output instructions can be that you say in and then give a port number, okay, or a device number, right? Say we generally call it a port number, or out, that means output the content of either a memory location or a register to a port number. But the input output for complex devices is a bit more complicated, and we'll take up that discussion when we discuss that input output devices in our lectures. Okay. Now then let's come to the other operations. There are some system control operation. Okay. We call it system control operation. Now some of them are, say, let me use this, enable interrupt, disable interrupt, okay, and wait for interrupt. Okay, this is essentially call it enable this is disable interrupt, and this is wait for interrupt. Now in the first two lectures we said that when the CPU wants that some I/O devices to work, the CPU need not wait for the I/O devices to complete its operation. What it can do is that it just sets the I/O device into motion, okay, initiating the job, and then it starts doing its own job. When the I/O device has completed the operation, the I/O device then interrupts the CPU and tells that that job it has been completed. Then the CPU can do whatever the data that has been supplied by the input device, or if it's output device, possibly the data has been consumed by the output device, and the CPU decides the next course of action. Now, the thing is that, say the CPU has given a job to be done by, say, a output device. Okay. Now, the CPU may be doing certain very important job, and it may not like that any device or any other person, I mean any other machine, subsystems, etc., interrupts it. In that case, what it can do is that it can disable all interrupts and saying that it does not want that it be interrupted now. And similarly, after disabling interrupt, when the CPU finds that it can once more entertain interrupts, then it can enable the interrupt once more. Therefore, you see that this disable interrupt and the enable interrupts are used so to say that whether the CPU wants to be interrupted, okay, or can afford to be interrupted or not. If the CPU cannot afford to be interrupted, then it says it's disable interrupt, or if the CPU can afford to get itself interrupted, then it enables the interrupt. Okay. Now that is the situation for the enable interrupt and the disable interrupt instructions. We'll have some occasions possibly of using these two instructions later on. Okay. Now wait for interrupt is a situation where say that CPU has given some job to be done by another subsystems or some input output device, but the CPU cannot proceed any further, okay, until and unless that job is completed. Okay, for a simple example, say program has given something to read, okay, but that program, the CPU that is executing, needs the data immediately before it can proceed once more. Therefore, you can see the CPU cannot proceed once more, and therefore CPU has to go to a wait state, okay, executing these instructions that wait. Okay, it will now wait till that interrupt comes, okay, and from the input device the data is that accepted by the CPU, and then the CPU can proceed once more. Okay, now this can be used for waiting, keeping the CPU in a wait state. Okay, once more we will have some occasions of discussing where these wait instructions can be fruitfully utilized later on. Now let us come to another set of instruction which we call that branch group. Okay. Now we said that say a CPU is executing an instruction many times, and as we know the CPU executes instructions one by one in a sequential order, right? Now after executing several instructions in a sequential order, the CPU may want to go out of the sequence and start executing some instruction which is away from the normal sequence, either in the forward direction or say in some backward direction. Okay. For example, the high level statements that we have say if A greater than B, then we do something, else we do something. Okay. Now this is essentially ultimately when it's converted to machine language is equivalent to that branching out from a normal sequence of execution depending upon what is the result of this comparison. Okay. Now sometimes the high level language have a code which says that go to say some label 1, that is an unconditional branch to label 1. Therefore, you see that we can either have a conditional branch or we can have an unconditional branch, okay, from a particular point of execution. Okay. Now we have several instructions to do that. One is a jump instruction. Say for example, if there's a jump instruction, say jump followed by some address say 0500, then say this is a jump instruction is here, then on executing this jump instruction, the control will automatically will be jumped to 0500 location if it is here, or 0500 location if it is on the lower side of the address space. Okay. Now this is jump, and there can be conditional jumps also. I hope you remember that say we have few flags, okay, like say carry flag, sign flag, overflow flag, and the parity flag, okay, overflow flag and the parity flag that we discussed when we had been discussing that arithmetic that the computer can perform. Okay. Now, depending upon the status of this flag, which can be either 1 or 0, the jump can take place. Okay. For example, we can have an instruction say jump on carry, right, which means that I'll jump out provided the carry bit is 1. Okay. Similarly, we can say jump on no carry. These we call the conditional branch. Okay. Conditional branch instructions. Similarly, we can say jump on sign, jump on no sign, or rather jump on sometimes called positive, jump on negative, jump on positive, right? Similarly, we can have jump on overflow, jump on non-overflow, okay? Jump on parity, jump on no parity. Then parity is even, then we call jump on even parity, and we can call the jump on odd parity, okay? Now, these are the conditional jumps or conditional branches. Jump is an unconditional branch instruction, okay? Now, there are other branch instructions also. For example, we can say instead of a jump, sometimes it's called a branch instructions, BRN. How far a jump instruction can take the control depends upon what is the address that I can put on the along with the jump instruction. Okay, that we'll talk when we come to that addressing modes. Now, another instructions sometimes are there. We call it a skip instruction. What the skip instruction does is that, so for example, you have the skip instructions here, and you have one instruction here. Say, for example, this instruction is move register 1 to register 2. Then the skip instruction skips the next instruction and continues the execution. The CPU continues execution from the instruction here. That means it skips immediately next instruction, and the control comes to the instruction. Control comes to the instruction which is next to next. That's called the skip instruction. Now, this branch and skip instruction can be and have to be used whenever you have to control the flow of control of execution of a program, right? Now, as you know that we use that subroutines or the functions. In that case, the control has to flow from one point in one program or one function and goes into the beginning of another function, and the control should come back to the point from where the control flew out. Okay, this is called naturally subroutine call or the function call. Correspondingly, naturally, there should be a machine instruction which will be able to handle this, and such instruction is called jump to subroutine. Okay, we'll discuss the jump to subroutine in our next lecture.